given the function f such that r maps onto r, f of x equals 3e to the minus x on 2 minus 4, and we want to find the inverse function. And then part 2, we want to find the values of x when f of x is equal to the inverse function. Notice that f negative 1 here means the inverse function, not 1 over f of x. A little bit of theory behind all of this is that if f must be a 1-1 function, then it will have a function which is a function, and the inverse is denoted by f negative 1. As I said, the reciprocal function, 1 over f of x, is not the same as the inverse function. So the function must be 1-1 for it to have an inverse function. If it's not a 1-1 function, then we need to restrict its domain so that it is a 1-1 function. There are some extra properties then of inverse functions. When we have the inverse function, the domain of the inverse function is equal to the range of the original function and vice versa. So the domain of the function is equal to the range of the inverse function. Furthermore, if we want to obtain the rule for the inverse function, then we must swap x and y, rearrange, transpose to make y the subject. If we're going to graph the function and its inverse, then they will be reflections of each other along the line y equals x. So that would mean if there are points of intersection, they must occur along the line y equals x. Alright, so let me define my function that we're going to graph it. So I will go Menu, Actions, Define. I'll call the original function f1 of x equal to 3 times e. So we have to get the button for the exponential, and it's minus x over 2. So we'll have a control template here, control divide. X over 2 minus 4. Make sure you get out of that bit and have minus 4. Alright, so that's defined my function. Alright, now if I want to have the inverse function, we have to swap x and y and solve for y. Now, that can be done in a very smart little manner here, because if I just go Menu, Algebra, Solve, if I solve f1 of y equal to x for y, then that's already transposed, rearranged, and done the whole problem for me. So not only has that given me the inverse function as 2 log e 3 over x plus 4, it's also told me that x is greater than minus 4. So it's also told me the domain of the inverse function, which is the range of the original function. Notice that the domain of the original function, f1 of x, was r for real. Alright, so I want to plot both of these functions now. So I'll go Menu, Actions, Define, and this time I'll call it f2 of x equal to, press the up arrow, and just do a little bit of editing. We don't need that because that will be its maximal domain. We can just delete the y equals there. So I've defined f1 and f2. Also note that there is a function on TI-Nspire which will tell us the maximal domain of a function. This function is not available from any menus, so it's only available from the catalog or the book command here. So if I press the book command, and if we weren't already on the word domain, we could just press the letter D and scroll till we found the word domain. So the syntax from the book is often useful because it tells us what we need to type in. It's domain, expression, variable. So press enter. Well, let me just show you then the domain of the function f1. These are my only variables here, so if I typed in var, I can just press X and type that in. So the domain of f1 is negative infinity to infinity, which is r. Let's go up and press up arrow again, and let's just edit this one and just change that f1 to f2, and it tells me the domain of f2 is x greater than negative 4. Okay, so very useful commands for finding the maximal domain of a function. Alright, so let me go to a calculator page and press Tab. Now, these functions are already defined on the calculator page, so the graphs page knows about them. So when I press Enter, there's my function F2. Let's just press Tab again. Alternatively, I could have pressed Control G. That would do it as well. So there's my function F1 of X. Again, both of these are in black. So let me go Control Menu and change the line color to say, one of them to say red. Alright, another graph would be nice there is the line Y equals X. So let's press Menu, Graph, Entry, Edit. There are lots of ways I could do this. I'll go for a function, say F3 of X. I'll just type in X. So that's the line Y equals X, and we can sort of see that both of these functions are reflections in the line Y equals X. Alright, let's come back to the calculator page to find the coordinates of the points of intersection between the function and its inverse. So the original function is F1, the inverse is the function F2. So if we go Menu, Algebra, Solve, where the points of intersection are the points of intersection between the graph of F1 of X, where is that equal to X? Or F2, F3 there, I could have said, it doesn't matter. So let's solve that equation. We'll get one value of X. Notice that that also has to be the Y coordinate as well. Let me just go up and reissue that command again, but this time change that to F2. Now we should get the same answer when I press Enter. Sure enough we do, because where F1 of X is equal to X is the same as the point where F2 is equal to X. The points of intersection between the function and its inverse must be along the line Y equals X. What about if I was to solve where the function F1 of X is equal to the function F2 of X? Then you would think that that's also that same point of intersection, minus 0.337. But in fact, we get three solutions to this one. One of them is minus 0.337. That makes sense, but we've got two other points of intersection as well. Perhaps this needs a little bit more of a point of investigation here. So let's go back to our calculator page. We can see that there are two other points of intersection and the point of intersection which is along the line Y equals X. So if I want to find graphically the coordinates of the points of intersection, let's go Menu, Analyze Graph, Intersection. Now the calculator is not sure which graph we're talking about here because we've got three graphs. So let me just say the first graph, which is F3, and the second graph, which is this one, for example. We have to have a lower bound and an upper bound. Alright, so there's the coordinate of the point of intersection, minus 0.37 and minus 0.37. That makes sense, that was the point there. But it appears that there is another point of intersection. So let's repeat that. Menu, Analyze Graph, Intersection. This time I'll choose this graph and this graph. And again go for a lower bound and an upper bound. So although it's got minus 4 there, let me just press Control Menu and change the attributes on this one so that we see it is minus 0.37997 and 18.2. Alright, let's just have a look. Let's do that again. Go Menu, Analyze Graph, Intersection. This time we'll choose the graph F2 and the second graph F1 and do a similar point here. Well, again, it's got minus 4 here. Let me change the attributes of that one. Alright, so we see that the point of intersection, that point lies on the line Y equals X, but these two points of intersection are interesting because their X and Y coordinates are interchanged. So the X coordinate of 18.2, the Y coordinate of minus 3.997, and here I've got an X coordinate of minus 3.997 and a Y coordinate of 18.2. So when we come back to the calculator page, that's exactly what happened here. Minus 3.997 and the other two values as well. So graphs and the functions for the inverses, if they are to intersect, they can occur along the line y equals x, but they could also occur in some other points which are also x, y, and then sort of y, x here. So their points are transposed as well.